Hello students, in this video I will explain how we can minimize finite state machines. To understand minimization of finite state machines, we have to know the concept of equivalent and non-equivalent states. These equivalent and non-equivalent states are otherwise known as indistinguishable and distinguishable states. Once we identify this concept of distinguishable and non-distinguishable states, we can apply any of the two theorems which are displayed. We have two theorems for minimizing the FSMs, that is Equivalence Theorem and Myhill-Nerode Theorem. Any of these two theorems can be used in order to minimize FSMs. In this video, I will explain only Equivalence Theorem for minimizing FSMs. In the minimization of FSM, or we could also call it as a finite automata, we are considering only deterministic finite automata or deterministic finite state machine. This is a process of reducing a given finite state machine to its minimal form. And in the minimal form, the DFSM has to contain only the minimum number of steps or states. The DFSM in its minimal form is called as a minimal DFSM. How can we minimize DFSMs? There are two methods for minimizing DFSM. One is by applying the equivalence theorem and the other is by using the Myhill-Nerode theorem. This Myhill-Nerode theorem is also called as table filling method. Before we apply the concept or method of minimization, we first have to know the concept of distinguishable and indistinguishable states, also known as non-equivalent and equivalent states. We first take the definition of indistinguishable states. Consider some two states, say P and Q, which are in the finite state machine M. Now these two states, P and Q, which are in M, if we consider M as our finite state machine, consider we have two states. This is P and this is Q. Now these are considered as equivalent. When we have a set of strings W which belong to sigma star, and these strings W drive M to an accepting state from both P and Q states, and the strings W drive M to a rejecting state from both P and Q. Non-equivalent states or distinguishable states. Again we consider the same concept, that we have got two states P and Q which are in the finite state machine, and these are called as non-equivalent states or distinguishable states if for all strings W which belong to sigma star, then W drives M to an accepting state from P, but W drives M to a rejecting state from Q, or vice versa. This is, consider there is some string S. Now one transition, consider we write transitions with delta, and we have got a state P on S. This goes to an accepting state, and the same string is given to state Q, but this goes to a rejecting state. In case such a scenario occurs, then we call them as non-equivalent states. Whereas if both go to accepting or both go to rejecting states, then we call it as indistinguishable or equivalent states, because we cannot distinguish between the states. They are both considered to be equal. But in case they give two different outputs, that is one goes to accepting state and one goes to rejecting state on a particular input, then we call them as distinguishable, or we can distinguish between the two states. They are not considered as equal. And for a DFSM to be considered as minimal DFSM, then we need to have all the states as distinguishable states. They should not be equal states. Now, for applying this DFSM minimization using equivalence theorem, Let us consider a DFSM D represented as D equal to Q sigma delta Q naught and F, and this DFSM D recognizes a language L. The minimized DFSM will be represented as D dash, which is written as Q dash sigma delta dash Q naught and F dash, and this is constructed by making use of the equivalence theorem as I explain in the future slides. The first step in the minimization of DFSM using equivalence theorem is to eliminate all dead states and inaccessible states. We have got two types of states here, that is dead state elimination and inaccessible state elimination. What are these dead states? Dead states, we have earlier heard the term as trap states. So dead states are actually trap states. These are non-final states and they transit to themselves for all the input symbols in sigma. And then we've got inaccessible states. This is the second type of state which has to be eliminated. These inaccessible states are those which can never be reached from the initial state. Once we eliminate these two types of states, then our DFSM is ready to be minimized. The next step is to draw the transition table for the given DFSM. The transition table gives us all the transitions of all states on all the input symbols in sigma. Step 3 is to apply the equivalence theorem. Now, in the equivalence theorem, we first consider a counter variable k, and we initialize this counter variable k with value 0. Therefore, k will be equal to 0. Then we divide the set of states capital Q into two sets. What are these two sets? One is a set which consists of all the non-final states, and the other is a set which consists of all the final states. This is iteration number 0. We could consider it as iteration number 0. This partition can be written as P0. So in P0, partition number 0, we take the entire set of states Q and we divide them into two states, that is accepting states, these are final states, and the non-accepting states are non-final states, and this partition is called as P0. The fourth step in minimization of DFSM is to increment k by 1 and then find the pk partition. Now in step 3, what did we do? We took the set of states Q and we divided it into two parts, that is accepting states and non-accepting states. So in step 3, we had a counter value k is equal to 0 and we called the partitioning as P0. So in this partition, we had two set of states. One is a set of all accepting states and then we had a set of all non-accepting states. In step 4, we increment this k value by 1. So what is the partition value? Now it becomes P1, that is pk, otherwise called as pk. And how do we get pk? It is by partitioning the sets which are in the level pk minus 1. So we take this set A of all accepting states, set NA of all non-accepting states, and we partition those states. We consider each set of pk minus 1, and in each of the sets we see whether we have a possible set or pair of states within each set which are distinguishable. And in case we find distinguishable states, we partition them into different sets in pk level. So again we take here, if we are to consider this first set, we check whether we have distinguishable states and we divide them. Here we check whether we have distinguishable states and divide them. Therefore, two states Q1 and Q2 are considered as indistinguishable in partition pk for an input A if delta of q1 comma a and delta of q2 comma a are in different sets in partition pk minus 1. It becomes very clear when we see an example, and this video has got an example which explains the minimization of DFSM. In step 5, we repeat step 4 until no change in partition occurs. That is, when pk is equal to pk minus 1. Therefore, if we are having pk minus 1 and this has got some 4 partitions, and we've got pk also has got 4 partitions, and all these partitions have got the same states inside. The first partition has got the same states, the second partition has got the same states inside, the third has got the same state, and so on. Then we stop our partitioning, and all those states which belong to the same set are considered as equivalent. So these states which are within the partition 1 are considered as equivalent states. Again, the states which belong to partition 2 can be considered as equivalent states. Then we merge all the equivalent states. By merging, we write them as a single state. Instead of multiple states, we consider them as a single state. Therefore, the number of states in the minimal DFSM will be equal to the number of sets in the partition pk. So if this has got 4 partition, then the DFSM will have 4 states, where one is the start state, then we have a set of final states. We shall take an example DFSM and apply equivalence theorem for it in order to understand minimization. Now this DFSM has got 5 states, that is Q0, Q1, Q2, Q3 and Q4. And what is the input alphabet? Sigma is equal to A comma B. The start state is Q0 and the final state is Q4. This is the preliminary data which we have looking at this DFSM. Now this has to be minimized. We have to lessen the number of states which are available in the DFSM. Therefore, what is the first step? The first step is to eliminate all dead states and inaccessible states if any are present in this DFSM. Do we have any inaccessible states? First we check whether we have dead states. We do not have any dead states. Then we see whether we have inaccessible states. So to check inaccessible states, we are talking about all the states which are not reachable from the start state. So you can see from Q0 we can go to Q1, and from Q0 we also can go to Q2. From Q1 we can go to Q3, from Q3 we can go to Q4, and from Q4 we can go back to Q1. So we can see that all the states which are in this DFSM are reachable. Therefore, we do not have any inaccessible states. Therefore, given DFSM contains no dead states and no inaccessible states. The second step in the minimization of DFA is to draw the state transition table. Let us write these transitions. We've got 2 inputs A and B, and we've got 5 states. We start with the start state Q0. Since this is a DFSM, we know that for every input there is only one state transition which occurs. So Q0 on A goes to Q1 state, and Q0 on B goes to Q2 state. Next we take Q1 state. Q1 state on A, it's a self loop, so remains in Q1, and Q1 on B goes to Q3. Next consider Q2 state. Q2 state on A goes to Q1 state, and Q2 on B, it's a self loop, remains in itself. Next take Q3 state. Q3 on A goes to Q1 state, Q3 on B goes to Q4 state. Q4 state, which is our final state, on A goes to Q1 state, on B goes to Q2 state. So these are our transitions which occur on the DFSM. In the step 3, we apply the equivalence theorem. We know that in step 3, we take the set of states Q and divide them into two parts, that is accepting states and non-accepting states. We have a counter k equal to 0 and we call this partitioning, that is partitioning into accepting states and non-accepting states as partition P0. Let us consider the DFSM here. So the states which we have are Q0, Q1, Q2, Q3 and Q4. Among them, Q0, Q1, Q2, Q3 are the non-accepting states and only Q4 is an accepting state. Therefore, our partition P0 will be equal to Q0, Q1, Q2, Q3 belonging to one set and Q4 belongs to a different set. So one set of accepting state and one set of non-accepting states. Next, we increment the counter by 1. Now k will be equal to 1, which means that the label of partition becomes P1. We take P1. In P1, what do we take? We take pair of states Q0, Q1, Q0, Q2, Q0, Q3, Q1, Q2, Q1, Q3 and Q3, Q2 and check for equivalence. So first we will consider Q0, Q1 pair. So delta Q0 on A and delta Q0 on Q1 on A. It goes to the same state Q1. And Q1, in this case Q1, since it is Q1, you cannot distinguish. Next we take Q0 and B and Q1 and B. So what happens here? Q0 and B goes to Q2 and Q0 on B, Q1 on B goes to Q3. Now we take these output states to which there was a transition, that is Q2 and Q3, and we check where they lie in P0. They lie together in the same set. Therefore, we can consider them as equivalent states. So Q0 and Q1 are considered as equivalent states. Next, we consider the next pair Q0 and we can consider Q0 and Q1 pair, Q2 pair. So Q0 and Q2 both go to Q1 on A and both go to Q2 on B. So Q1 we cannot distinguish, Q2 also cannot distinguish. Therefore, we can write that Q0, Q1 and Q2 are equivalent. Next, we take the pair Q0 and Q3. And Q0 on Q3 on B. Here it goes to the same state in both the cases. Here for input B, it goes to two states, that is, one is state Q2 and the other is state Q4. Check where they lie in P0. They lie in two different sets. Therefore, we split Q0 and Q3. Therefore, Q0 is in one group. Therefore, Q3 will be in another group. We need not check for other combinations such as Q1 and Q2 because Q1 and Q2 are in the same group. Since Q0 is equivalent to Q1, Q1 will be equivalent to Q2. Therefore, we need not check. And then we complete this partition P1 by the last group which was remaining. Next we take partition P2. How is this done? By incrementing counter K. Now it becomes 2 and we call the partition as P2. In partition P2 we take the pair of states Q0 Q1 and then we can take Q0 Q2 and Q1 Q2. So taking Q0 and Q1 both go to Q1 on A and they go to two different states Q2 and Q3 on B. We check where Q2 and Q3 lie in P1. They lie in two different partitions. Q2 is in one partition, Q3 is in one more partition. Therefore, Q0 and Q1 are split into two partitions. Therefore, in one partition we have Q1 and in the other we have Q0. The Q3 and Q4 remain as it is in the partition because we do not have to compare them with any other state within the set. We finish Q0 and Q1. Then we take Q0 and Q2 state. Now Q0 and Q2. Q0 and Q2 go to Q1 and here also you can see it is Q2. Q1 and Q2 are in the same set in the previous level. Therefore, Q0 and Q2 are considered equivalent. We do not have any comparison, therefore we can close the P2 partitioning like this. Next we consider the next partition. Here we increment the counter K is equal to 3 and now the partition naming becomes P3. For P3 we do not have pair of states here, we do not have pair of states here, we do not have pair of states. So this remains as it is. We have only pair of states in the first partitioning. Therefore we take Q0 and Q1. Q0 and Q1, this is Q2. Q0 and Q2 go to Q1 on A and go to Q2 on B. Both the states go to the same state for an input, which means that you cannot distinguish between them. Therefore, we group them together. And you can see this partition P2 and this partition P3 is the same. Therefore, we stop our theorem here, partitioning theorem here. And we conclude that we have 4 partitions. And what are those 4 partitions? One is a set of states Q0, Q2 together. And then we've got Q1 in a separate partition, Q3 in a separate partition, Q4 in a separate partition. We get 4 partitions, that is Q0, Q2. This was one set, and we had Q1 in one set, we had Q3 in one set, and we had Q4 in the other set. And these two states will be merged together and considered as a single state. The minimal DFSM will look like this. Q0 and Q2 will be merged together because both the states will go to the same state on input A and both the states go to the same state on input B. There is a different state transition for the other states. The minimum DFSM drawn by merging the states can be relabeled. So here you can see that from 5 states we have minimized it to 4 states. And we have labeled these 4 states as Q0, Q2 state, Q1 state, Q3 state and Q4 state. So instead of calling them like this, we can also relabel them and call them as A, B, C, D states. And then we write the D dash representation. which is a quintuple representation, Q dash, sigma, delta dash, the start state. Here we can tell start state, and then we've got a set of final states. So this representation has to be written for all the problems.